So we're doing 6.4 interest today. And there's a formula for compound interest. But before I write that down, I think you've seen it before, but before I write that down, I just want to explain what compound interest means. So if you have an investment, like maybe $2,000, if you put that in the bank and they give you interest for the first year, then they give you some money at the end of the first year. So then maybe you have $2,010 in your account. So then for year number 2, they're going to pay you interest on the 2010, not just the original 2000. So they're giving you interest on the interest they've given you. And that's called compound interest. So that's what this formula is for. It's assuming that, and this is the way all investments go, is once they give you interest, then that's your money, and then they give you interest on that. So the formula for that is A equals P, and then 1 plus R over N, and then to the NT power. So it's a little bit tricky to tell the difference between my R's and my N's. So this is an R on top of the fraction. That's an N, and that's an N. So N appears twice. Okay, so let me tell you what all these letters stand for. The P, the word that it's standing for is principal, but it's the amount that you started with, the investment starting amount. So P is the starting amount. The fancy term for that is the principal. Okay, then of course R is the interest rate. And so usually interest rates are given in percents, like 2%. But this needs to be in decimal form. So if the interest rate was 2%, then you would put 0.02 up there. All right, and then the N is the number of times each year that interest is given. I guess maybe better, interest is paid. So the number of, N stands for the number of times each year that interest is paid into the account. So sometimes they do it at the end of the year. So they just give you a little bit extra at the end of year 1 and year 2, etc. So in that case, N would be 1. But usually it's monthly. So that means they give you interest at the end of month 1, month 2, month 3. So then N would be 12, because that would be 12 times a year. And then, of course, T stands for time, and that's in years. And then the A is how much money you have at the end, after all that time has gone by. Okay, so for example 1, we were having $1,000, and it's invested at 3% interest for 5 years. And we're going to find the amount in the account at the end. if interest is compounded. That means how often it's given. And for part A, we're going to do annually. So $1,000 is invested at 3% interest for 5 years. We're going to find the amount in the account at the end of the 5 years if the interest is compounded. And then we're going to do this a few times. So for part A, it's compounded annually. So that's like what I talked about first, where interest is given at the end of year 1. So for the whole first year, you just have $1,000 in the account. But then for the second year, you have slightly more than 1,000. And so you're earning interest on that slightly more amount during year 2. And then after year 2, they give you another little bit. So then for year 3, you'd have even a little bit more in there. Okay, so compounded annually means that they give you interest once a year. So that means the N is 1. So I've got $1,000 for my starting amount, for my P. And I've got 1 plus, and there's a 1 in the denominator, and a 1 up here, because we already discussed that the N is 1. Okay, then for the interest rate, 3% as a decimal is 0.03. So that goes here, that's the R. And then T is the time, which in this problem is 5 years. So you can just type all that in at one time to get the answer. So you got 1,000. So I'm getting $1,159.27. Remember, in calculus class, you always round to 3 decimal places, except I'm going to break my rule here because this is dollars and cents. But still, don't forget, 3 decimal places all the time on the AP test, right? Okay, so that means if you put $1,000 in the bank and you've got a 3% interest account, and they give you interest at the end of every year, you're going to have at the end $1,159.27. Okay, so now for part B, we're going to compound quarterly instead. So that means that they're going to give you interest at the end of every 3-month period. So at the end of 3 months, at the end of 6 months, at the end of 9 months, and then at the end of 12 months. So 4 times a year. So compound quarterly means 4 times a year, so the N is 4. Time is still 5, right? Interest rate is still 0.03. So the only thing that changed is this is a 4 now. Okay, now before we get the answer, you should have slightly more than $1,159, right? Because in this problem, you only had $1,000 for the entire first year. But in this problem, after 3 months have gone by, you have a little bit more than $1,000 because they give you interest after the first 3 months. So for the next 3-month period, you're earning interest on that little bit extra. And then after 6 months, they've put money in there twice. And so you're getting extra interest, even more extra interest during the 6 to 9 month period, and then even more from the 9 to 12 month period. So since they're giving you money more often, this is going to be a slightly bigger number than the $1,159.27. Does that make sense why that is? Okay, so I think some of you have all the number already, but type that in if you're not there yet. So yeah, this is $1,161.18. All right, so now we're going to compound monthly. So this is going to give us just a little bit more money, right? Because in this problem, you only had $1,000 for the whole first 3 months. But in this problem, you're going to have more than 1,000 during month number 2. And then you're earning interest on that during month number 2. So it's 1,000 times 1 plus 0.03 over 12 to the 12 times 5. Because monthly would be 12 times a year. And to be honest about the real world, all the interest is compounded monthly. So this is the most real life scenario as far as finances go. So I'm getting $1,161.62. So not very much more, right? 34 more cents, or 44 more cents. But the reason it's a little bit extra is because during month 2 here, you're earning interest on more than $1,000. Whereas on month 2 here, you're only earning interest on 1,000. Okay. Here's part D. This is daily. So now we're going to figure, this is a probably unrealistic account where they give you interest every day. So that means 365 times a year, right? So that'll be 1,000 times 1 plus 0.03 over 365 to the 365 times 5 power. So that's $1,161.80. I'm going to go ahead and put a few more decimals in, and I'll explain why in a little bit. So there's $1,161. It would round to 83 cents, but I want that extra digit there. I'll tell you why in a second. So about 20 more cents if they give you interest every day as opposed to interest every month. So now we're going to compound continuously. And what this means is they're not going to give you interest every day. They're not going to give you interest every hour. They're not going to give you interest every second. They're just going to be constantly giving you interest. That's what continuously means. Now, it takes time to hand out interest. So this is a concept. It's not actually possible to continuously give you money. So what we actually mean is figure out how much you would get if it was 12 times a year. Then figure out how much you would get if it's 365 times a year. And then figure out how much you would get if it was 1,000 times a year. And then figure out how much you would get if it was 1,000,000 times a year. So what I'm talking about is a limit, right? And I'm taking the number of compounding and sending it to infinity. So since it's not actually possible to constantly give interest, we're just going to see what happens if we make this n get bigger and bigger. We already sent it to 365, which is pretty big, but now we're going to send it to 1,000 and 1,000,000 and 1,000,000,000 and see what that's getting close to. Okay, so this goes way back to chapter 2 when we were just doing limit. There's a time sign here. And limit goes past multiplication. So you can take the limit of the first thing times the limit of the second thing. I'm going to include the 5 in just a second, but I'm pausing for a reason. So recall that if you have x to the 2 times 3 power, that's of course x to the 6th, right? You could write that as x to the 2nd to the 3rd. Right? This is a situation where you multiply exponents. We're good at going from here to here, not so good at going from here to here, right? I want to go from here to here. Because see, I have the n times 5 power, so I'd like it to be to the n power and then to the 5th power. So in this situation, you would multiply the exponent, so it would be the 5n power. Okay, what is the limit of 1,000? 1,000, right? Because this function outputs 1,000 no matter what. So if you plug in 10, it's 1,000. If you plug in 100, it's 1,000. If you plug in 1,000,000, it's 1,000. So the outputs are closer and closer to 1,000. All right, we had another limit law that said that limit could go inside a power. So that's why I wrote this like this, so that I could put the limit inside that. So this is the limit as n goes to infinity of 1 plus 0.03 over n to the n power and then to the 5th. So this step to this step, I put the limit inside the 5th power. But we had a limit law back in chapter 2 that said you can put a limit inside a power. Just like we had a limit law that said you can put a limit past multiplication. Okay, so this limit here should look sort of familiar. So let me show you one that looks more familiar. What's this limit? Anybody remember what this limit is? Yeah, it's E. So this was on Monday's assignment. You've made a table and this was getting closer to 2.7 and 2.71. This limit is E. Okay, then on Tuesday, they ask you to change this number to a 2 and to a 3. So does anybody remember, if this is a 2, what is this limit? It's E squared. So that was on Tuesday's assignment. And if that's a 3, then the limit is E cubed. Okay, so this limit here is E to the 0.03 power. So that limit right there is E to the 0.03. And then you could multiply those. So it would be 1,000 times E to the 0.03 times 5. So then you can use a calculator to figure that out. So that's $1,161.83. So this is what would happen if you compounded interest every second, and then somebody else said, okay, I'll give it to you every half second, and someone else said, I'll give it to you every quarter of a second. This is what those are getting closer and closer to. So that's called compounded continuously. Now, you can see now why I decided to make this 827. Because if I had rounded it to 83, you would have thought that this answer was the same as this answer. But you see that they're slightly different? Very slightly though. So giving interest daily is pretty much the same thing as giving interest constantly. But it is slightly different. Okay, so in the past you learned how to do compound continuously, but you didn't know what a limit was. So now it's important that you do it the limit way. Because this is a calculus class, and this is the only calculus so far in this lesson, right? So make sure you're doing calculus instead of some other thing. The other thing involved E, though, right? I don't want to talk too much about it because then people will do it that way. So I want the limit way. But it's not a coincidence that that other way had an E in it. This is a crazy famous limit. This limit is E. Okay, so I did kind of glaze over a fact here. When we did interest daily for 5 years, what did I leave out? Are there 365 days in every year? No, some years have 366 days, right? Some years are leap years. And in a 5-year period, there would have been at least one leap year. If year 1 was a leap year, then there would have been 2 leap years in this 5-year period. So I decided to ignore that to make things simpler. But I bring that up because a few years ago, I got a letter from my bank. I still have it. So this is interesting. It's dated December 15th, 2009, so it's pretty old. This is from Fifth Third Bank. It says, Fifth Third Bank periodically reviews customer account information and transactions for accuracy. We want to make you aware of an error that we made in your certificate of deposit account during 2008. During a recent review, we determined that the daily interest rate accrual was incorrect for accounts that were not open on February 29th, 2008, which was during a leap year. Consequently, you are entitled to an interest credit of 19 cents. So they sent me a check here for 19 cents, which I haven't cashed yet because I think it's more interesting to keep it. I don't really need the 19 cents. Well, some days I do. But anyway, that's neither here nor there. So they also tell me that this information will be reported to the IRS. So they're making sure that I'm going to pay taxes on my 19 cents. Ridiculous. So anyway, in the real world, apparently they pay attention to leap years, because this is a real letter that I got that said they had made a mistake when they forgot about the leap year. There you go. There's my story from 2009. So let's go on to example 2 now. So in this problem, a $2,000 investment is compounded annually. And the interest rate is 2.25%. Question is, how long will it take for the investment to double? Okay, so we've got $2,000, so that's the P in the account. And it's 1 plus. Okay, so this is 2.25%. So for the decimal, you have to move it 2 places, right? So that would move it past the 2 and then past the 0. So it's 0.0225 for the R. And then, since it's compounded annually, that means once a year. So n is 1. And then the question is how long. So that means we don't know the time. But it wants to know, when is the investment going to double? So if it starts out with $2,000 and it doubles, that means you would end up with $4,000. So we want to know what t will make this equal 4,000. So now we've got to solve this. So first thing, we're going to divide this 2,000 to the other side. And 4,000 divided by 2,000 is 2. And then this will be 1.0225. I just divided that by 1 and added 1, right? So that's where I got the 1.0225. And 1 times t, of course, is t. Okay, now how do you deal with an equation that has a letter upstairs? Yeah. Natural log of both sides, right? We take natural log of 2 equals natural log of this. And the reason we did the log is because of the rule for logs that say when you have an exponent inside, it can be a multiplier in front. So we didn't really know how to deal with this when it was upstairs. So the log now allows it to bring it downstairs. We've got ln of 2 equals t times ln of 1.0225. And then you divide both sides by the ln of 1.0225. T So that means it's going to take 31, a little bit more than 31 years for the $2,000 investment to double to 4,000. Okay, so just a little bit of reminder about what's been going on. In a lot of the problems, like radioactive decay problems and other problems, they've said that the rate is proportional to the y value. So how do you say that mathematically? If the rate is proportional to the y value, what's the fancy math notation for that? Yeah. KY. Yes. So it's proportional to the output variable. So this is the fancy math way to say the rate is proportional to the y value. And we've separated the variables on this many times. Why is it necessary to separate the variables here? Because the output variable is sitting there, right? So whenever you have the output variable in the derivative, that's when you have to separate the variables. I imagine number 7 threw you off last night because it didn't have the output variable in it. And you just assumed you were going to have to separate the variables. You didn't need to separate the variables because it was just 11, right? You with me? Okay, but this one, it would be necessary to separate the variables because there's a y in the output. Okay, so we've separated the variables on this many times, and you have to know how to separate the variables on this. But since we've done it so many times, we now kind of know that this is always going to lead to this. Which is an exponential graph, right? You see how the letter is upstairs, the T? The very first one of these we did, it was 2 to the x at the final answer. This was 0.69 times y, and it turned out to be 2 to the x. So anytime you have the rate proportional to the y value, it's going to be exponential. And that means that the graph looks like this. That's an exponential graph. You see how the rate keeps getting bigger? The rate is the slope, right? You see how the rate keeps getting bigger and bigger and bigger and bigger? I mean, people throw around the term exponential all the time. You'll hear it on the news. They don't know what they're talking about. What exponential actually means is that the rate keeps increasing. And that's what they were concerned about with the coronavirus, right? They were concerned that not only were the cases going up, but the rate at which the cases were happening was going up. That's more concerning, right? That how quickly people are getting it is increasing. So that's exponential. The rate is increasing. And what's going on here is, if the y value is 2, then the rate is something times 2. But if the y value is 4, sorry, that's an x value. The y value is 2, sorry. If the y value is 4, then it's still 4 times that same number, so the rate is bigger. So the rate keeps increasing. That rate is a lot bigger than that rate. That's what an exponential graph is. Eventually, this has to turn around, right? In a real life situation, usually. It's not just going to keep going up and up and up and up. If it's an exponential, it does keep going up and up and up. Everybody doing okay? All right, that's all for today.